Recording. Hello, Dion.
Hey, Dion and Rich's excellent life adventures.
Hey,
Great.
man. Here we are. After screwing around for months and years thinking about this, we're finally doing it.
Finally doing it. I'm sure that all of the millions of people out there are really excited to hear our stories.
Hey,
All of
I, I,
my
ch-
followers.
I checked in my last podcast. I got 5 views,
Whoa.
four of which were me. So we're moving up in the world.
Nice. Nice.
So I
So
think,
what do you want to talk about?
well, I think we should talk about our life. I mean, this is our first podcast. We've never done this. This is a sample, but it's been so great getting to know you, Dion. I mean, to think I would know someone from Namibia who lives in Amsterdam and talk to him 4 times a day, it's a little weird, don't you think?
Yeah, it's a little bit weird, but yeah, likewise, it's been a really interesting journey getting to know you and the stuff we're building and the little adventure we're on. It's fun. I mean, it adds spice to life.
And I always thought that you would be an excellent podcaster because you've got the perfect voice, and this is proven in this call. Absolutely proven.
Yeah,
You
my
sound great.
my mom also said that. She always said like I've got a face for radio. It's great.
You've got a total face for radio. You should, Howard Stern. These guys are screwed. Joe Rogan. These guys have no future amongst our 5 followers. So since this is a demo podcast, you notice that we're working on, little graphic things that look pretty and so forth. So I hope that you, our many listeners, will appreciate the fact this is just in development. So please appreciate that. I don't know what we're going to talk about really, Dia. We can talk about almost anything. We were just talking about how to design systems for tiny startups. Full disclosure, Dion and I are working in a tiny startup with, I don't know, what, 7 people, 8 people? We're in our little company.
Yeah,
We
around
can't
eight.
tell you what we're doing because then we'd have to kill you. But we can talk in general about the lessons and how you make maybe the parameters. We're remote first, right?
Yeah.
And how many locations do we have? Where are people working out of right now? Let's do the list. So there's you in
Yeah, we
Amsterdam.
have Amsterdam, Tokyo, Seattle, and California, and Idaho, New York. Did I
Some,
miss any?
sometimes
Sometimes
Tokyo,
Hawaii.
sometimes Tokyo, sometimes Hawaii.
Yes. Yeah.
So we're
Yeah.
first up. And since you don't have 1,000 people, figuring out how to debug these complex systems, and just to give our listeners a sense, we're building a robotic system with advanced AI and recognition and all this other stuff, and it's a mountain of code. I mean, it's everything from the little robots all the way to the back end processing in the cloud, and it's really hard to design these things, don't you think?
Yeah, it's there's a lot of moving parts with these complex systems. It's something that I've spent my entire career up to now building. Although I haven't touched the machine learning part nearly as much up to now. And until I met you guys, it's been mostly on the automation side and the robotics side and um, safety critical robotic design, right? So how do you make a robot that doesn't fail and that doesn't fall on its face all the time? And it's the same thinking you can extend to anything from unmanned aircraft to autonomous driving cars and everything in between.
Well, and
Um,
you've really been doing this autonomous stuff since you were like a baby, right? I mean, what was your first robot?
my first robot was probably this little modular robot I designed. So I did everything from scratch. I made the PCBs. And back then, after you design a PCB in the software called Eagle, it's open source, very simple. I think you could only do 2 layers back then. So you design the circuit board and then you print the circuit board out with black ink on white paper. And then that goes into an acid bath that eats away all the copper and just the tracks stay they stay behind. And then you hand solder all of the things.
Okay, I just
So
want to stop you right there. You are kidding me. That is unbelievable. I thought ordering a Raspberry Pi out of a catalog was advanced. That is nuts. And then did you write the software too? Did you do it all yourself?
yeah, this was on using microchips DSP. I think it was the MSP 430 or something I used, but it's basically um this company called Microchip, they have a MIPS architecture that they released, and they were in competition with ARM for a long time. And I decided to use the MIPS thing because it was just easier to source through DigiKey back then. And the chips were smaller, and they also came in these big dip packages that you can just slot in, so it's easy to hand solder.
Yeah.
Um, and then it's just a matter of reading the data sheet and doing a lot of low-level C programming. But the robot was really cool. So it's basically a PCB about this big. And the idea is this PCB you can use as a module. So the PCB has motor drivers, so a little H bridge that I built with transistors, and then you've got the motors connected. And then the cool thing is you can have this one module, so it has two little motors, and you can stack them and connect them on a CAN bus. So each
Oh my gosh.
PCB communicate by a CAN bus, and you can build up a whole robot with 8 wheels or 4 wheels or 3 wheels. And then for perception, what I made a little PCB with an infrared LED and an infrared photo transistor. So when the photo transistor detects the infrared light, it basically pulls a pin high or low. I forget what it did, and that told the microchip there's something in the way. So I had an array of these things around my little modular PCB. So you can end up building a robot with anywhere from 4 to how many wheels you want, and it has infrared boundary around it. And then it basically did what a Roomba did. So it just drove forward. If it hit an obstacle, it would just turn 90 degrees to the right and then go forward again until it hit an obstacle. And then I put it in a maze and see if it could escape.
Okay. That is insane. I mean, that is so amazing. And how old were you when you did all this project? I just have this image of you you know, in a cafeteria doing all this work.
Oh, I think that was when I was 19 when I did
What?
that.
What?
Um,
That's crazy.
and
That's
I
crazy.
couldn't program, so I had to, this was before the days of YouTube, and there wasn't a lot of stuff available online. So it was a lot of trial and error and a lot of getting your hands dirty with things. But I've always loved playing with robots. I've done that, and then did a lot of things with unmanned aircraft and drone light shows, and it all just comes back to this like super complex system with many moving parts. There's hardware, there's software, and these days there's a lot of machine learning stuff. And how do you build a system like that? How do you architect it so that it's easy to find mistakes early, to find bugs early?
Yeah. Yeah.
That's normally the, the challenging part that I find with like super complex multidisciplinary systems like those.
Well, I think this is a good thing to talk about. I mean, how do you do that sort of work? And particularly when you go from that robotic stuff all the way to how do you build a large scale cloud system? I mean, you're talking about dependencies everywhere, don't you think?
Yeah, exactly. And um, well, you could go the monolithic route and just build everything in one massive, bundle. But then obviously debugging is hard to do, and it sounds so simple when you say it out loud, but it's so easy to forget, because sometimes runway as a startup is your enemy. Like even in a corporate situation, if you've got a product manager or a boss telling you that you need to deliver some feature by some time, um, obviously you want to get the quickest path to that result,
Yeah.
and that means using something that's maybe a completely baked in monolithic solution. And when something goes wrong, you don't know how to debug it because you can't really divide and conquer, which is why modularity is king. If you look at a monolithic kernel versus a microkernel approach, um, there's big benefits in going microkernel, where you can have the network stack fail and just restart the network stack, whereas the rest of the code is still up and running. Whereas if the network stack's built into the kernel, you don't have that
Right.
luxury.
And
Yeah.
I think you know this about me, Dion, but I'll just tell everyone else. So I have a terrible habit of writing everything that I learned down in a PowerPoint slide. One of my things. And I don't know, in the last 2 years we've worked together, probably 100 of these things. And so I made a slide deck on your lessons, and I think it might be fun to go through it. We're going to publish it in the show notes so people can just look at it. But and we're also going to try a cool new view we've never tried before. So let's try this. Hey, this worked! Oh my God, system design. And here we down at the bottom. I want to tell you we're very proud. Um, Not all of these things are exactly aligned yet, but we'll get there. We're trying to build a series of templates so we can have it. And now we are all Macedonians these days, aren't we, Dion?
Yes, Mastodon for the win.
Down with the birds. So you can reach Dion at Dion@nerdculture.de, which I think is the coolest of all of the I think they're called instances, the Mastodon instances. I'm on a much boring one called sigmoid.social. Actually, I'm on a bunch. But you can just check us out there. This is, by the way, the Dion and Tong Cast 01, first episode, 2nd of March. Is it 2nd of March? 2003. Or 2023, sorry. And here's a few things about system design. So in a nutshell, and Dion's going to go through these things, I think the first point is complex systems are really order n squared to debug. Maybe we can just talk about that a little bit. So if you've got a really complex system with a lot of dependencies, if you've got 2 modules, there's only one relationship, right? But if you have 4, how many interactions do you have? Well, it grows dramatically, right? And if you can turn it into a pipeline, if you have, say, 2 things, there's 1 dependency. If you have 4, there's only 3. Just think of it as a long pipeline going through, and it's much simpler to debug. Don't you think, Dion, we spend a lot of time trying to make everything linear in our little company?
Yes, because, as a startup, you have limited resources, but speed and flexibility is, those 2 things are your friends. So I think along with architecting your physical architecture, the actual product you're building, you should also think about how do you architect your team, because that goes along the lines of building culture. So if you have a loosely coupled architecture that's made up of reusable modules that you can swap in and out, you can also have people working individually on those modules. That leads to less, meeting overhead and less dependencies in the team. And the major upside is it's basically 2 birds with 1 stone, because it simplifies team dynamic. It makes sure that you're running really fast on the execution side, but also debugging in the future, maintenance, all of those things are greatly simplified. Because if you build one solution that's made up of, let's say, 100 individual reusable modules, then if the solution breaks, it's easy to identify the culprit and to swap out the broken module with something that's better, whether it's on your perception stack in the machine learning context, or if we talk about robot control, whether it's your navigation system that's doing your path planning, or whether it's your inner stabilization loops or your health and monitoring system, it really applies across the board.
Yeah, no, I totally agree with you because, I think Elon Musk, and you can talk about him, but he did once famously say, your software's designed like your org chart. So if you've got different divisions, then you basically create those modules. I'd argue that in a small company, you are your pipeline. So the more complex you make the flow, the more complex your organization is. And the simplest possible organization of n things, by the way, is put them in a row. That's just the simplest. And I think you're so right that once you put in a pipeline, you can swap modules. But in particular, if you're file-based for input and output, that means you don't have to run the entire pipeline to test things. Because I've seen a lot of systems where you have to bring up, this thing, the robot, this, and then you can finally test. It's so much better if you think about it as a series of chunks and it's file in, file out, because now you can test things in parallel. You can run things in parallel, right? So you've taken an order n problem, ordering the number of things, to an order 1 problem, in that you can have, say, you have a pipeline of 6 things. You can test all 6 things in parallel. All 6 people can run in parallel. Well, what does that mean? If I had a 7th module, actually my development time doesn't grow. I can just add another person. And if you've ever read F.P. Brooks and the Mythical Man Month, this is the big crisis. That adding more people, what does it do? It just slows the project down, usually by an order n squared, right? When you add
adding Yeah, 9 women can't make a baby in 1 month is what he famously said in
Yeah,
that book, right?
right. But in this case, if you've got a pipeline, the pregnancy thing is such a good analogy. But if you're trying to make a table and you can make the chairs, you can make the top separate from the leg, separate from that, adding another leg doesn't actually increase the development time. Just
Yeah.
someone makes another leg and you staple it on, and now you've got 5 legs. Um, I think one of the things that you really helped me with is this idea of just test and really understand each one. Assume perfection at the input, and then just debug very, very steadily. And I think you've done an amazing job in our company of doing that.
It's this is very applicable to machine learning pipelines and analytics pipelines, but you can really extend it to robot control as well. Um, but if we stick to the pipeline concept for a second, if you imagine like the raw data coming into your machine learning pipeline, we all know that we need to clean that data. So whether it's text data or image data, you need some sort of pre-processing to put it in a consumable state. But once that's done, if you imagine your whole analytics pipeline as a series of modules, if between the modules you have these, you can put storage containers or buckets in, like you're saying there, so you're file based. Now, when everything is running at full speed, the data doesn't spend a lot of time in the bucket. It's consumed really quickly. So the buckets, it's like buffers. They're there's very little data in it when everything is running well. But when something breaks, they will start to fill up because nothing is consuming from the bucket. So you can monitor the buckets to see, oh, my pipeline is failing at this point. And then you can branch to a different part of the pipeline that uses a different series of modules. But it's very easy to not only debug, but also to build in intelligent analytics around that. So you can build kind of a self-healing pipeline if you have enough of these pipes in parallel and you monitor the depth of your buckets basically between your modules in the pipe.
I think it's such an important idea, and it works both in the cloud but also in the field. Like, when you're trying to test a robot, there's all these different pieces that are going wrong, and trying to figure out how to isolate each module is important in the physical world as well, don't you think?
Yeah, yeah, really important. And that's why when it comes to controlling physical systems like robots or cars or aircraft, it really helps to understand the physical system really, really, really well. And then building modules around the physical characteristics that you understand. If you look at an aircraft, for example, it has what's called the short period mode and the longitudinal mode, stability modes in the longitudinal axis. And if you really understand, you don't need to be an aerodynamic expert, but if you understand where the forces and moments come from on that vehicle, then you know which sensors you need to add to sense, and you know which feedback paths to develop to stabilize those modes. Whereas you could go the other route and you can just you can add a bunch of sensors on your vehicle, your robot, whatever you have, and just run it through a massive machine learning network. But if something goes wrong, you don't know where to fix it. Then it's this whole monolithic network that's failing, and you've got no insight into why it's failing.
Yeah.
So rather reduce the problem set, and you could still use machine learning, but really constrain it so that it's easy to see where things are going wrong, where in the pipeline or where in when you're controlling a vehicle. Is it in the inner loop dynamics? Is it the stabilization part? Is it your path planning part? Is it perception?
Yeah, no, and I think the other thing that you taught me is it's really important to make the actual test in the physical world um, very controlled. So if you're just trying to test, like say flight control, it should be in an open field where there's no magnetometer interference and so forth. Try to isolate those variables. So don't start with the most complex environment possible. Start with the simple environment first.
Yeah, and build up from there. Like working with controlling physical systems, it's very similar to thinking, it's very similar way of thinking when you're developing pure software applications, thinking in terms of modularity, thinking in terms of reuse, thinking in terms of if I have a bug in my software, we all know, just change one thing at a time. Don't change multiple
Right.
things at once, and um, try to remove bits of the code until you're really down to that specific function or class or module that's misbehaving. And it's the same thing with physical systems. I guess there's just sometimes more inertia working with physical systems because it just takes longer and it's sometimes just harder to physically bolt something, you know, take the bolts apart and ripping things out and then developing a harness around this specific subsystem or this module
Oh my
that's
God.
misbehaving.
Tell me about it. I mean, that is so complicated because the physical world doesn't let you isolate the way you can in the logical world. Super
Yeah.
difficult. And then I think the last thing is, once you have these pipelines, you can really try to make these goals linear. I mean, I think, a lot of times there's Kanban systems and so forth, and there's this huge mess of projects. But, once you have a pipeline like this, you can just improve each piece one at a time, and you don't have to think about all the complex interactions. I've seen so many projects where it's like, okay, change the input filter. That means you got to change the output filter. You got to do this. And so you have to bring the whole thing up. But once you pipeline it, then you can just say, let's just improve this module and let's just fix
Yeah.
that. Don't you think?
Yeah, 100%. I also like that approach. And I mean, there's still so many things that I need to learn, and there's still so much that I don't know. But what I have seen up to now is at least keeping things linear and keeping it simple. Um, it helps because the problem has irreducible complexity in and of itself, because you are trying to do something that is really complicated, like trying to control a robot that doesn't hit a wall all the time, or something that needs to reliably take off a vehicle that weighs a ton and land on a runway every single time with 95% success rate. I mean, that's hard to do. And I guess as technologists, the it's always so tempting to over engineer, to add a lot of extra shiny bells and whistles. And I think that you know complexity compounds in a system over time, and
Yeah.
if you keep complexity low in each module, the overall complexity should be manageable at the end of the day.
Yeah. I mean, I think if I were to summarize this, is that complexity sucks.
Yeah,
Things that are ordered and squared suck. And I think spending a lot of time on engineering out the complexity ahead of time is sort of the key, don't you think?
yeah,
It's really important to think about this ahead of time.
yeah,
And if you can think about it ahead of time, then you get to the point where, yes, you can solve each problem individually. And then I think that the management becomes a lot easier because now you're just talking about, let's get team one to focus on planning, or let's get team two to focus on output, and it just becomes an easier management challenge, don't you think?
I agree. I am wondering though, how does this scale beyond a startup size? Because both of us, we've also worked in corporate environments where there's larger teams, and arguably also larger products being developed. But I don't know. I've also seen small teams and startups. If I look at what we're doing, for example, we do quite a lot. There's a lot of stuff that we're developing because we're reusing and we're carefully making these technology decisions. So I'm wondering, like, is this something that you can apply in larger corporate environments, or is the management layers, are there just too many of them? What's your take on that?
Oh, I think it completely applies. I mean, a large corporation is just a collection of smaller projects, and
Mm,
you can get killed by the complexity. So,
mm,
and I've always been a big admirer of AWS, for instance, where everything's basically a module. You get on there and there's like 1,000 different things that are going on, and they're all independent, and then you compose them. And you have to remember the systems that we use today, which is almost all Unix based these days, fundamentally, Ken Thompson and Dennis Ritchie focus completely on modularity. Right? Write the
mm,
smallest possible program that does the smallest possible thing. And the trick is don't create these gigantic chimera tools.
mm,
So would you rather have a tool that just concatenates some prints and also a separate program that lists things? That's much better than one gigantic file minder with 100 flags. But
mm.
I think the challenge in modern technology is to keep that in mind. And when I look at the
Yeah.
really successful projects, they are very modular, right? If you look
Mm,
at the really successful companies that are at maximum scale, they've got a compute engine that does this thing. They've got a Kubernetes framework that does orchestration. And you thinking about the layering and making it independent is very, very important. So no, in
yeah.
everything from infrastructure as code to GitHub repos. It's all about managing this massive complexity. I know. I think it's very, very important. If you're in a big company, you think, well, I'm a big company, it has to be complicated. I hate to tell you, it just ain't true. Right?
Yeah.
You just have to drive for it. Now, what happens though is it's always nice to imagine module X helping module Y, and the fallacy there is you just create a gigantic dependency, right? And it's oftentimes I see where you have two things that need to cooperate. It's like 4 times slower to get the product in. And I've worked on lots of projects that really ended up never shipping because you couldn't get the complexity out because A depended on B. It shall remain nameless, but I was once in a meeting where um, essentially 1,000 libraries called each other and the thing wouldn't compile because actually module 1,000 called module 1. So it was actually not possible to compile it because everyone assumes that everything else is stable. And that's where you get into real trouble. So I think this pipeline thinking is pretty important.
Yeah,
Okay.
I can see that. That sounds like typical dependency hell. This happens often if you've got too many header files that you're cross-including, or you're including a library everywhere. And I think you raised an important point, like when you start to scale from your startup, because obviously, we're going to grow and we're going to add more people, and then we need to make sure that we keep on developing the product in this way where we architect the architecture to be modular so that we end up with less dependency in the team itself. But I think on top of that, as you grow and the system grows, each developer should develop their module very defensively. So you should assume that, okay, so you're developing a standalone thing that has no dependency on someone else, but also assume that whoever wants to use your module is going to try and abuse it.
Yeah.
Don't assume that you will only be fed image data if you're working on a pose estimator or a SLAM system,
Yeah.
right? Assume that someone can send you accelerometer data and maybe their shopping list. So that typically works really well if you're like super defensive and make sure that that system can survive out in the wild. That has a better chance of surviving longer term in the whole
Yeah.
system,
Absolutely.
as opposed to something that makes assumptions on the type of data it's going to consume.
Yeah. And in many ways, the way you can think about it is, there's sort of infrastructure you can depend on that's always going to be there. So there definitely has to be a layering, right? So if you've got a module that you need to know what the hierarchy is. Like that thing is always going to be called, but you don't want A calling B calling A, right? This is
Yeah.
what causes a lot of problems. And then the pipeline is actually a trick, because what it says is I'm only dependent on the guy ahead of me,
Yeah.
right? So you've actually reduced dependencies dramatically because you're basically saying I don't know what's going to happen behind me, and I'm leaving that. But I'm really, in the worst case, you're creating a directed acyclic graph. In the best case, you're creating a pipeline. Then you only have
Yeah.
one producer and one consumer. Now, it turns out it's almost impossible to keep the DAG, just make it a pipeline. But thinking that way helps because if you think about it that way, a directed acyclic graph is just two pipelines stapled together. Right? It's usually something where you have multiple inputs or you have to merge multiple outputs. But still, the dependencies, you can read the table from left to right. And so
Yeah.
you have a chance of having it work.
Yeah.
Well, I think that's about all we have time for in our little test setup. This is
Yeah, this was a great first little episode on this, and honestly, like why I'm having fun doing this with you. I honestly don't really care who listens to this or who watches
yeah,
it.
me neither.
This is a nice little record for us to keep track of, like our thinking at this point of where we are right now, because we've learned so much over the last 2 years, that I've been on this journey with you guys, and we it's not going to stop here. So it will
No,
be so funny to look back 5 years from now to this video and laugh at all of the stuff that we thought was important and all of the lessons we still needed to learn.
yeah, I know. We're gonna make fun of me and the order n square thing. People are gonna make fun that it was stupid. We know that, but of course, that's why we're just trying to improve for our future selves. That's the
Yeah,
goal. Well, thanks for
exactly.
listening to the excellent adventures of Dion and Rich. We've had a great time talking to you, Dion and Tom, and we'll be back next week. We're gonna try to do this as a regular thing, don't you think?
Yeah, regular thing. Once a week, we just talk about anything and everything that comes up while we are trying to build a robotics startup.
Yay! Maybe ChatGPT could be in our future next. Thanks, Dion.
Ooh, might be.
All
Thanks,
right.
Rich.
Bye
Till next
bye.
time.